Today we're going to continue looking at section 5.2. And we start with just a statement. Functions with the same derivative differ by, at most, a constant. And if you think about that for just a second, if you come up with two functions that are different from one another, that have exactly the same derivative, the only thing that could have been different is the constant term. If the constant term is different, it doesn't matter because when we take the derivative of the constant term is 0. So another way of saying this in a more formal way is if f prime of x is equal to g prime of x at each point of an interval I, so it may be true in one interval and then not true someplace else, then there is a constant, capital C, such that f of x equals g of x plus c for all x in that interval. Now, if they really are the same function, c would be 0. But the difference between those functions can at most be some constant. It can't be any term with a variable in it at all. So this allows us to do an idea like this. Find the function f of x whose derivative is cosine of x and whose graph passes through the point 0, 3. So we're saying f prime of x is cosine of x. So then, what's the simplest thing that f of x could be? Not sine. Yes, sorry, my fault. So it could be sine of x, but it could have any constant attached to it, right? So we'll just say sine of x plus c is the general form of that. We'll talk about it more in just a second. And then it says it goes through the point 0, 3. Well, that means that f of x is 3 when x is 0. So in this case, and in a lot of cases, but not all, by any stretch of the imagination, c comes out to be 3. So my function f is sine of x plus 3. It turns out most of the time when you're dealing with polynomials, the constant turns out to be whatever this is, the y value is, provided that the x value is 0. And it works out for certain trig functions. But notice if f of x had been cosine of x, since cosine of 0 is 1, that's not going to work out. Okay, what we have just done is found an antiderivative. We took a derivative and went the other direction. So a function, capital F of x, is an antiderivative of f of x if capital F prime of x is equal to f of x for all x in the domain of f. The process of finding an antiderivative is called antidifferentiation, which is one of the longest words, real words at least, that I know. It's too long to make it a Scrabble word. Unless someone put different and then you added the eation and then on another turn you added the anti. So let's look, find all possible functions with a derivative f prime of x is equal to 1/2 x to the 1 over 2x to the 2/3 power. And then find the function that contains the point 8, negative 5. Well, first of all, I've got to rewrite this derivative. F prime of x is going to be 1/2 of x to the negative 2/3 power. So if we're thinking about undoing the product rule, you're like, well, to get this, what did we do? How did we get the negative 2/3 if we were taking the derivative of something?
You put the front back to the power.
Right, but my question is just this. How did the negative 2/3 come about?
Because you subtracted 1, so now you need to add 1.
Right, so now we need to add 1. So that's going to be x to what power?
2/3. Positive 2/3?
1/3.
No, 1/3.
No.
Negative 2/3 plus 1, 1/3. Now, if we took the derivative of x to the 1/3, what would we have?
1/3 x to the negative 2/3.
Right, so we've got the x to the negative 2/3 part, but we don't have the 1/2 part, do we? All right, now when we take the derivative of this, we multiply by 1/3. So here's what I typically do. I keep the 1/2 for right now. And then I don't want the 1/3 when I bring it down to make any difference, do I? So what do I need to multiply by? What can I multiply 1/3 by so that it doesn't make any difference? By 3. So, you were saying, Connor, that we should add 1 to the power?
Mm-hmm.
Absolutely. And then what we should do, instead of multiplying by the exponent at the beginning, you multiply by the reciprocal of the exponent at the end. So this is going to be my f of x plus some constant. And then I'd probably clean that up, make it 3/2 x to the 1/3 plus c. And one of the great things about this is once you have found an antiderivative, you can always check your answer by taking the derivative. What we're going to find is that whereas with the derivative, there were all sorts of rules for finding the derivative, when we get to doing antiderivatives more, we're only touching on it right now, but when we start doing them more, you start finding, there's not a lot of rules. It's kind of figure it out so that it makes it so that when I take the derivative of my antiderivative, I get back to the original. All right, so now we want to go through the point 8, -5. So -5 is equal to 3/2 times 8 to the 1/3 power plus c. What is 8 to the 1/3? 2. Times 3/2 is just going to be 3. So it's -5 is equal to 3 plus c. So subtracting, we get -8 is my value of c. So f of x is 3/2 x to the 1/3 minus 8. That's an important idea. Like I said, we're just going to touch on it right now, but we're going to spend a lot of time figuring out how to find antiderivatives of things. All right, on the back, here's some other really big ideas. First one is increasing and decreasing functions. So if you talked about these in previous classes, you probably talked about them graphically. And you said when the graph is going up as I move from left to right, the function is increasing. And if it's going down as I move from left to right, the function is decreasing. And that is absolutely true. It's a little more technical than that, though. So if I have f as a function that's defined on this closed interval from a to b, and x1 and x2 are any points in that interval, including a and including b, f increases on the closed interval if for x1 less than x2, f of x sub 1 is less than f of x sub 2. Right? The function value got larger as the x value got larger. And then f decreases on that closed interval if when the x value gets larger, the function gets smaller. Okay? And one of the things I struggle with personally is I really probably shouldn't say smaller. I really should probably say lesser. Right? Smaller sometimes isn't the right idea. It's actually less. So I'm still working on that. By the time I retire, I'll probably get it right. So this is super important. The corollary, this is one of the corollaries of the mean value theorem. And it says that if f is a continuous function on the closed interval from a to b and differentiable on the open interval from a to b, and you're like, hey, I recognize that. That's the qualifications for using the mean value theorem. So it has to meet those qualifications. Two things. If f of x is greater than 0 for each point on an open interval from a to b, then f increases on the closed interval from a to b. And we've already talked about this some. When the derivative was positive, the function is increasing. We talked about this when we did related rates, right? Okay? We're just formalizing that, and we're going to use it in some problems. Likewise, if f prime is less than 0 at each point on the open interval from a to b, then f decreases on the closed interval from a to b. So you may be like, why do we do this open interval, closed interval thing? Well, what's going to happen is, in most cases like this, we're going to find that the derivative is equal to 0 or doesn't exist at a or b. And then, but that doesn't exclude it from our interval of increasing and decreasing. Let me just point out one thing. For us, increasing and decreasing is always on an interval. Now, occasionally people will talk about something that's increasing at this point. And what they really mean is they mean any interval that contains this point, it's increasing. All right, so let's take a look at this function. Where is the function f of x equals x cubed minus 4x increasing, and where is it decreasing? Well, what we're going to do is take the derivative. That's 3x squared minus 4. And by the way, I should look at the function first. Is this continuous everywhere? Is it differentiable everywhere? Yes, so I don't have any worries about it fulfilling the qualifications for the mean value theorem. And what I'm going to do is I'm going to set that equal to 0. Because what this is going to do is going to allow me to divide up all x values into intervals where f prime will be positive and f prime will be negative. So add 4, divide by 3, I've got 4/3 is equal to x squared. Take the square root. X is equal to, remember there's a positive and a negative, 2 over the square root of 3. Now, what I do to help me visualize this is draw a number line and go, okay, on this number line, something important could happen at negative 2 over the square root of 3 and positive 2 over the square root of 3. Notice because this is a continuous function, the intermediate value theorem applies, right? So I know that f prime is 0 at each of these places. So that's a potential point for f prime to change from positive to negative or negative to positive. It's not always going to happen, but potentially it could, right? When you stop at a stop sign, you could throw it in reverse and start going backwards, right? You don't always. Fact is, you rarely do. But you could. But you could also just keep going and cross over that street. All right, so what I'm going to look at is what is the sign of f prime in each one of these intervals? And the easiest way to do that is just to pick a point, substitute it into the derivative, and see if it's positive or negative. If your result is positive, then throughout that entire interval, f prime is positive. All right, so for this, and you're like, what the heck am I supposed to do? This is negative 2 over the square root of 3. Well, I want something less than that. Well, how about just negative 2? Right? I think that's pretty obvious that that's less than this. So if I substitute negative 2 back into the derivative, I'm going to have negative 2 squared is 4 times 3 is 12 minus 4 is 8. That's positive. So everywhere on this interval, f prime is positive. And you can do these pretty quickly sometimes because we don't care about its actual value when we're checking. We only care about whether it's positive or negative. So that means that f is increasing on this interval. All right? So on the interval from negative 2 over the square root of 3 to 2 over the square root of 3, what would be an easy point to check? 0. Substitute that in, we get a negative. So f prime less than 0. So f is decreasing on this interval. And if we pick something larger than 2 over the square root of 3, like 2, we get the same result we got before when we substituted in negative 2, mainly that f prime is positive. So f is increasing here. So f is increasing on two intervals. The interval from negative infinity to negative 2 over the square root of 3, it includes that right-hand endpoint. And from inclusive of 2 over the square root of 3, exclusive of infinity, because, well, infinity is not really a number, so we can't close it in. And f is decreasing on the closed interval on both ends from negative 2 over the square root of 3 to 2 over the square root of 3. At this point, occasionally a student will look at that and say, well, does that mean that f is both increasing and decreasing at negative 2 over the square root of 3? No. Remember what I said a moment ago, that when we're talking about increasing and decreasing, it's on an interval. So talking about a particular point doesn't make any sense. Again, we occasionally do it because you're like, yeah, it's increasing everywhere on the interval around that. Okay, any questions about that? Okay.